Okay. And the way you can tell if we're recording or not is this little bar right here. Right where the red dot is, if you see live, that means it's recording to YouTube at the moment. So if it's gone, then I forgot to do it. It would be rude for you to suggest, hey, Mike, could you turn that on? I'll be happy to do it. Almost there. They tell us not to start until 7 sharp, so I'll be doing my best with that. But even though I can't start until 7, you folks are always welcome to ask questions at any time. Well, I think we can get started. Welcome back, everyone. So for today's class, our goal is really to just introduce the website, run through the syllabus a little bit, and we shouldn't take too much time with introductions. And we'll go through, well, 2.1 is kind of an introductory section in and of itself, but we should be able to finish these notes too while we get started. But before we start anything at all, any questions that folks would like to begin with? Okay, well, welcome to Calculus. Pretty much what we're going to be doing here is extending on the things that your tools and ideas you've picked up in college algebra, trigonometry, about the ordinary functions like logarithms, polynomials, trigonometric functions. Start talking about other topics like differentiability, integrability. Those are just weird sounding topics. But to a really strong degree, when this says tangent problem, we're really going to be talking about lines and how lines approximate curves. And that'll be the theme for pretty much the first half of the course. So 2.1 is a great place to get started. And Freddie says, I came to Rendezvous Hall 332. I'm the only one here. Well, you're in the wrong place. Sorry, Freddie. We're in the Idaho Falls. So if you'd like, I can talk to you about that after class, but you can continue to hang on in the Zoom and that'd be okay as well. Other questions at the moment? Okay. So let's, I guess, first open up the syllabus. I don't want to go through the whole document because it's really, really verbose. Some of this stuff I didn't write, and that's at the very, very bottom of the document. I encourage you to take a look at this information here. This is provided by the university. A lot of these resources you have already paid for example. A lot of them can be profoundly helpful. So if you've never seen these things before, I'd say read it at a high level the first time. If this is another semester for you, maybe just browse through it to look for anything new. At the very top is just the pertinent information. I'm Mike Jacobson, and class, or on these days, it's kind of a weird schedule, but we make it work. Monday and Wednesday feel all right, but going to Wednesday and Thursday, it can be a grind. We just get through it. To help out, I'm going to assign homework on Thursdays, and they'll be due the following Thursday. So there'll be a 1-week turnaround, so you can put some flexibility in your schedule. Because this is a night class, sometimes it can be hard to get through some of these things. And that's just one way I'll try to help out. For contact information, my phone number is there. You're welcome to call, text, any of that kind of fun stuff. It is silenced a lot of the day, and so probably I'm most responsive would be here on the email. I always have this email open, so if I'm not responding to you right away, I'm probably just out doing something. And the next time I'm at my computer, that browser to that email is always open. I'll get to you as soon as I can. One thing I want to mention about emails as well is You can email about just about anything. Maybe you're starting on a homework problem and you say, hey, Mike, I just don't know what's going on with problem 17. Here's a picture of what I did. Send me anything you can and I'll be better able to help you. And I can help you through email in that kind of way. Or it could be other stuff like I'm missing class this day or so on. I'll be very happy to help out. If that email is sometimes really, really late, if you're working at 2 a.m., then I'm sorry, but that you're still welcome to send an email. It's not going to wake me up. And you're getting your thoughts down so I can see it in the morning. So don't feel like there's an off hour for email. The moment you have a question, that's probably the best time to compose your email. Aside from email, that's again pretty clunky. If you want help face-to-face, I'm available to help right after class. But these are the official office hours. This one is in my tab office from 4:30 to 5:30, and I'm going to be there Mondays and Wednesdays throughout the whole semester. You don't have to book it with me. It's walk-in office hours. If you feel like it's helpful, you could say, hey, Mike, I just want to come in to talk about this topic, and I'll kind of know what we're getting into, but it's by no means required. You can just walk right in through the door. I'll be happy to help out. These office hours are in this Math Center, the Student Success Center, they like to call it sometimes. Room 220 is on this building. It's in about that direction over there. It doesn't start this week, so I put here temporarily on the Moodle website, those hours, 4 to 5 p.m. Tuesdays and Thursdays, they're going to be starting on next week. I'll be in that room at those times, no matter what. If there's ever an interruption to these things, I'll be the first thing I'll do is let you know that something's going on. Well, that's how to get help, how to get a hold of me. Any questions at all so far, folks? Okay, moving through the content. This is a pretty traditional class. I'm not going to be using any online course homework system. It's really going to be paper and pencil or pen and pencil, that kind of thing. And the textbook itself is this one right here. This is the 9th edition, and it's a custom edition as well by ISU. If you're buying this through the bookstore, keep in mind you are paying extra. The good news is it's the right book, and you just donate it to ISU essentially. If you decide to save some money and buy used, you can go backwards on these editions. The 8th edition would work. The 7th edition gets a little unstable compared to the current one, but it would work. I'd say if you're about to buy a textbook, maybe send me the link so I could take a look at it. Because even if it says 9th edition, there's more than one version of the 9th edition. That's extremely annoying. You might have to pay attention to this ISBN right here as well. So be careful buying a used book. It can save you a great deal of money. If you are using used editions, I will be posting the actual homework problems, so you don't have to worry about copying it from someone else's book. Other questions about the textbook so far? Okay, we're 5 minutes in, so we're getting through this. I'm going to skip the course objectives because, in my opinion, it doesn't make sense until you finish the course. So this is a good place to come back to see if we hit those ideas. And like we mentioned for homework, it's just going to be on a week-by-week basis. In fact, let's pause right here. We go back to the Moodle website. Everything really goes right through this website here. First page is just informational kind of items. You'd always want to turn it to the current week, this week. This is going to show you what notes we're about to go through. You could print them ahead of time if you like. This is the PDF version. Above, you can also get them as a Word document if you prefer to tinker it with them that way. And this is the assignments that will be posted. They're posted in kind of a strange way. Assignment 1 is not official until we actually get to Thursday. That's why you see coming soon here. I know about what problems I want to assign, but I just want to make sure we get through the content. I don't assign problems we didn't talk about. That's never very fun. So once we get to Thursday, you'll see all these are problems officially here, and the due date is going to be August 31, a week away from the upcoming Thursday. Does that make sense to folks? Awesome. And that's pretty much how it's going to repeat. When you come back to class on Monday morning, there's a note here about things that are happening in the schedule. You'll see assignment 2. We'll say something about section 2.4 or 2.5. We'll just be building them out as we go. I'd say the most effective way to really nail this class and get through it is the moment you see an assignment, this one says, just do exercise 5. It's an introductory section. Best time to do it is right away. I realize you can't necessarily go home and do them right away. This is a night class. Everyone has things going on, family, other jobs, and that kind of stuff. Kids can sometimes really suck away all your available time. If you get through this before we meet next class, I'd say that's the gold standard. Hard to do going from Wednesday to Thursday. Sometimes we get a little bit behind, but the more caught up you are, the better shape you are going to be in absorbing this information. So that's where the homework assignments are going to be posted. For submitting your homework, well, I'm really imagining most people are just going to write it down on ordinary paper, maybe lined paper. If you could keep your section together, that'd be helpful, and just submit it on Thursday. I don't really have much of a spot here, but probably right here would be a great spot. Also, if you're not in class that day for whatever may have came up, you can take a picture, cell phone picture would work, a real scanner, even better. Just scan your entire assignment and you can email it to me as well. I'm happy to accept your assignments digitally as well. Other questions so far about the homework assignment, submissions or otherwise? Okay, we'll talk more about these little details as things become due, like the assignment. We'll talk a lot more about the exams as we get closer to them. But for the moment, we're just kind of going over surface details, just so we know about what we're about to do. Let's go back to the syllabus. There's other information here about showing step-by-step solutions and things like that. Also, at the very end of the semester, I am going to be dropping the lowest 3 assignments. And the reason I do that is things happen, life gets kind of crazy. And so that just helps us for if that ever happens to you. Other coursework can get in the way of those kinds of things. Scrolling down, I highlighted this in yellow because for me, this is one of the bigger changes, how I taught the class in the past to the present. This year, I'm going to be allowing the TI-30XA or the TI-30X2S calculators on exams. So we'll have open calculator exams, and these are just for really fast computations. A lot of people probably have already used this calculator or this calculator. If I go to the Moodle website, I think I have a link here. Calculators, there it is. And this is about what they look like. I would probably recommend this one for an exam setting in this class, only because you can put a bunch of stuff in all in one line. It's a little bit faster. But if you've used the TI-30XA a lot in other exams, let's say a chemistry class, you're just fast with it, it's just fine as well. I tend to write my exams so that they don't really need a calculator. So anything that might make you reach for this is just going to be maybe the last part of an exercise on an exam, for example, something pretty small. Any questions so far, folks, about calculators or other business? It's a closed to graphic calculators, correct. So just either these two here. Okay, well, let's go off to, I think we're getting through the syllabus pretty quickly. Next thing down here is a breakdown for how we're going to assign points in the course. Homework is really where all the learning really comes in. It'll be worth exactly 25% of the class. If you're doing well on homeworks, if you get, say, a slightly lower homework grade, but you come to office hours, figure out what you missed, you're going to be really well positioned for the exams. They'll be worth 45%. And if you're doing great on the exams, people typically do very well in the final exam as well. As we get closer and closer to any exam date, what I'll be pointing to and what you'll notice on the Moodle website, say exam 1, there's a lot more information is going to appear right here. I'll tell you the exact coverage. I'll upload things like review material, things of that nature. So there'll be extra resources to actually study and prepare for that exam. All those resources will be finalized a week before. So say Thursday of this week right here, you'll know what's on exam 1 and you'll be able to print out the actual review materials. So that's how the exams will go in this semester. We're only going to have 3 different exams. They'll average to, well, I guess they're 15% each in that case. And we'll have the standard letter grade scale here. So yeah, go ahead. Oh, let me take a look. This should be for all exams.
Yeah, so is that one side or?
Oh, sorry, I understand. It'll be front and back. Yes. Yeah, you could, if you like, have it handwritten like you're saying, front and back. I'm okay with people printing them out. So if you open a Word document, you can really cram some things in there. But keep in mind, I've seen some amazing, like you almost have to get some imaging hardware notes, but they may not be super easy to use. So keep that in mind as well. Organization is just as important as cramming it all in at the same time. But other questions about that? Okay. Well, going down, I think the only item we haven't really covered, other than the resources at the bottom, we should definitely check out. Here's our day-by-day schedule, and usually we stick pretty close to it. It's not a requirement. Say, for example, if section, I don't know, 4.9, let's pick on this one. This one was just a really nasty section, and we need to take an extra day. We'll move the schedule aside and make that happen. We don't have reviews before exams, except for the final exam. We'll have about a day and a half, and 6.5 is a small section as well. And so that's essentially our day-by-day schedule. Any questions at all so far, folks? Okay, well, that was 13 minutes. I think that's about as fast as I usually go. On the first day of class, I think I just talk fast because I haven't been working since the 6th of May, so I'm just a little rusty. So if I start talking too fast or it just sounds like a word salad, never rude to say, hey, Mike, what did you say? I'm sorry. Could you go over that again? I'll be happy to do so. But I think that's our run through the syllabus. Were there any items folks want to discuss in more detail? Okay, going through the first page of the Moodle website, there's not too much more to discuss. I'll be using this as a calculator in class. So that's the Desmos. It's just a fast environment to calculate something like the TI-30XA, or if we need some graphics, pretty good environment for that. On actual exams, I'm not going to ever ask you to graph anything. So anything we produce here, it's for us. It's for illustrative purposes. If an exam question needs a graph, it'll just be provided on that actual exam itself. We discussed calculators aloud on exams. We'll come back to some of this information as it gets closer to the pertinent time. These two here are more just informational. So if you want some motivation on what's calculus all about, why would you want to study it? Why does my program need it? That's a good place to go. And this one right here, I think could be very valuable for our class, how to study calculus, really just math in general. And this is a really old website, so it looks funky, but this is a legendary website, the Paul's Online Math Notes on Lamar University. He has a really long blurb on how to study math. He's been teaching it for a very long time. And he has even more things to discuss here, different links. So I think this is a great place to get some information or motivation. If you feel like your studying just hasn't gotten you the grade you wanted in the past, you might just need to refine a couple things. And here's a great place to do some reading. But this Paul's Online Notes, again, it's a pretty legendary website. You click right here, you can review algebra, calculus 1 through 3, differential equations. It's all here. The fact, if you run through this side-by-side art course, this is a really great way to learn calculus. You get a different take on how some of these topics are ordered and presented, different presentation. It's all the same kind of stuff. If you feel, for example, gosh, I'm getting rusty on, let's see what he's got here. How about logarithms? We'll use logarithms, exponential functions, trig functions. You could click right here and just get a really fast fresher up on this kind of stuff. Let's see, what does he have? Logarithm functions. They'll give you a discussion on what they're all about. They'll probably eventually show you some formulas you might need. And on all these things, you can go to the very bottom. Let me move some things around. Oh, no, it's up at the top. You can click on practice problems and just get more and more practice on this website with solutions built in. So even if you don't use it too much for this class, if you know you're taking a lot of math classes, it's probably a good site to come back to some point in your program. So that's the purpose of those two links there. The Zoom link is, if anything crazy happens, I mean, California just had a hurricane and a magnitude 5 earthquake, so they have class out. If that happens to us, I'll probably be on Zoom administering the class. After class is over, what I'll be doing is not on that very night. I usually have to get out of here, get the rest of my night going. But on the following morning, probably before 10 a.m. on Tuesday, I'm going to upload all of our recordings, and it'll just be dropped right here. It's empty at the moment since nothing's been uploaded. But we're all recording now, and that's where you'll see all the lectures. So that's pretty much the Moodle website. Every time I put down a PDF right here, I'm also going to duplicate it in Word format, like we mentioned. So if you like to print them out or just download them to work digitally, that'd be a good location to go. And I think I ran out of things to say. Any questions or comments so far, folks? Okay, so this was meant to be a pretty fast introductory because we're not doing anything too crazy. I don't have weird discussions to go into like how to do Alex or WebAssign. Those are kind of strange places to be. Instead, we're going to go right to section 2.1. Now, these are the PDFs, and all the PDFs are formatted to be essentially like worksheets. If you see me doing something weird and clicking around real fast, this is just my thumb drive and it's duplicating Moodle itself. I keep things in Word as we write on them. And after the lecture's done, after these notes are completed, I'm going to save these as a PDF and just overwrite this right here. So eventually this is just going to turn into a bunch of resources on different problems we've done in the past. So let's take a look at 2.1. And I think at this point, we're ready to get started. So this is our first definition. And definitions, especially in a calculus class, can get technical. Part of our goal in getting through this class is knowing how to actually read the mathematics so we know what it's even saying. So let's read through it and see just what's going on. It says, let f denote a function. The tangent line of the graph of f at the point a f of a is the best linear approximation of f near the point a f of a. And there's another definition down below for secant line. So that's our definition. And one thing I want to mention is in a math class, and really many other classes, not just math, engineering, chemistry, biology, sociology, and so on, looking at reading a definition, it's almost useless, sadly. To really read a definition like this, we have to be extremely active. And the textbook can almost do a disservice. They'll give you a beautiful graphic right here, you're just eyeballing it. But it's better if you cover that up. Just look at the words and try to duplicate what you're seeing here as best you can. Maybe peek at their graph while you're at it. And this, I promise you, will force you to absorb this information, whether you want to or not. You'll start dreaming about it the more you actually illustrate these definitions. Let's start right here. It says, let f denote a function. Well, we're going to have to graph that function and look at other graphics around it. So from right there, let's start by doing this. I'm going to put everything in quadrant 1 right here, just so it doesn't interfere with the axes, but you can draw your function however you like. I'll let start right here, so a solid dot. It's an increasing function, and then it tapers off and just goes right here. Put another solid dot. So the whole domain goes from A, let's not use A, it's already used once, or it goes from here to wherever this number is right here. So that's our function. It just said f, but you could say y equals f of x if you prefer. We'll be using loads of different kinds of notations for functions, sometimes just the name, sometimes the function notation. Other times we might just call it y. It all just depends on the context. So we have a function going. The next thing it says is the tangent line of the graph of f at the point a f at a, well, let's maybe start right there, is the best linear approximation of f near af of a. To me, when I read that sentence, that's the most confusing part, the coordinates af of a. Let's throw that on our graph. I'm going to put my a right here once I select the pen. So a just has to be somewhere in the domain from this location to this location on the horizontal axis. Once we put down a location, this will be the point f of a on the y-axis. So that's our output value. We want a tangent line to occur right exactly here is what the definition is indicating. Now let's focus on this part. It says it's going to be the best linear approximation. So we're drawing a line near the point af of a. So we want a line to represent this curve as best as it's feasibly possible. Sounds like a hard ask, but we can try. So let me zoom in here a bit and give that a try. Any questions first so far in the diagram? Okay, let's zoom in on this just so I can attempt to be accurate. This could be a little tricky. I get rusty with this digital pen stuff after summer vacation. So if I want to make this line as close to the black curve as possible, I might draw it kind of like this. Just let's make that dot a little bit bigger if it feels like the line's too high. And that's my line. When it says best linear approximation of f near af of a, what's meant there is We zoom in enough right here, it should become apparent the black line and the green line are just getting closer and closer to each other. I probably have to zoom in a ton and the resolution is going to break down, but we'll actually demonstrate that with a real function through Desmos in our problems. Yeah, go ahead. Sorry, say again. You might be dealing with the secant line in that case. So it kind of just depends. Our curve itself, maybe it did something like this. I made it go down, but it could have instead came back up like that. Now it's crossed in 2 points like you mentioned before, but really we're only caring about right here, A, f of A. It's all about this local region that we're concerned about. So if it hits 2 points in a different way, we may be thinking about the so-called secant line very next. But does that help so far with that question? Awesome. One thing I forgot to ask is, I'm zoomed up at 150%. Is this readable to everyone, particularly in the back row? About around 160, 70-ish. Awesome. I'll try to keep it more on this higher end, around 160, 170. I zoom in and out a lot sometimes, depending on the graphics I'm doing. So if I zoom out to something that just is too blurry, never hesitate to say, hey, Mike, can you zoom in? That's never considered rude. Okay, so we have a best linear approximation, and this is what we're referring to as the tangent line. Because it's a tangent line, it has an equation. It's y equals mx plus b. And we're extremely interested in that m right there. It's the slope of the tangent line. And let's give this a little bit of context. It's completely contextless, right? Excuse me. If this axis was, say, time, and this axis was distance, then that slope right there would be the instantaneous velocity. Much like if you look at the speedometer in your car. We're extremely interested in that slope m, and we've got a problem, kind of like what you're mentioning. I only have 1 point here. There's no way I can calculate the slope m based off 1 point of information, unless I do something extra. That extra is the actual calculus. Instead, we're going to be focusing on a secant line and see how we really get to that slope there. How are we going to compute the slope m with 1 point, a f of a? That point there is a bit of a trick. We first need the secant line to show how it happens. Any other questions or comments first? Okay, so let's go next to the second portion of the definition. It says a line that goes through a f of a, that's this point here, and now a plus h, f at a plus h, is called a secant line. So here's what's new when we say secant line. Let me just fix some highlighting here. It's this second part right here on the coordinates. If we add that to the illustration, let's start with a plus h. H itself could be positive or negative. So I'm going to consider it as a positive quantity. It's just supposed to be small. I'll put a plus h right here, meaning the actual h value is taken to be positive. We get a point on the curve, a little bit above. So there is a point right here, slightly above f of a, and that point is the f at a plus h itself. Let me just make my tick mark a little bit more precise here so it looks believable. So right at this height, little dots there to show it, is f at a plus h. So now we have 2 points suddenly, and that's good news for us because then we can calculate a slope. The secant line will go through a f of a, that point indicated here, and the second point, a plus h, f at a plus h. Let me zoom in and attempt to plot that thing. Our secant line then looks about like this. So our secant line is now in blue. And the thing to note about this secant line is, well, I don't know the equation of it either, but we know it goes through 2 points. We can calculate its slope, we can calculate its intercept, and we can discover the full equation right here. It'll be of the form y equals, I want to be careful when I write this m, It's not the same as this one. Maybe I'll put an extra decoration on it. I'll call it m hat x plus b. The only reason I put that up arrow, the hat portion there, is to just differentiate it from this one, different slope. You could use subscripts if you're a fan, call this M1 and that one M2. Now, let's now get to the punchline all here. That line's nice. And if that blue point was closer to the green one, if it overlapped, would you agree this slope here, M hat, would get closer and closer to the slope M here? I agree. I mean, the closer the blue line gets, or excuse me, the blue dot gets to the green one, the closer the lines overlap and become the same line. I can't make that blue dot exactly the green dot because we're back to the same problem, right? There's one point, you can't calculate the slope that way. But if h is small and that dot is close to that dot, we can at least approximate the unknown m, the slope of the tangent line, with this one, the slope of the secant line. So let's put this here. The goal is to estimate m using the slope of the secant line where h gets smaller and smaller. If we can do that, then you get better and better estimates of m. We want to know, where are those estimates going? What value do they settle on in the limit? And that idea of limits is really what chapter 2, where we're starting in, is all about. So this is the preview of why we're going to be doing multiple sections on this idea of limits. We want the limiting value of m hat as the secant line in blue gets closer and closer to the true tangent line. You can find that limiting value, then we know things like instantaneous velocity. We'll later call it the value of the derivative at a. Well, any questions or comments, folks, with that construction there? Okay, this is really the theme in calculus to a great degree. We know an awful lot about lines, y equals mx plus b. The curves are nasty things. Imagine solving an equation that's linear. That's really fast. It's just a step-by-step process. But if you have a nonlinear equation, every new system of nonlinear equations needs a new method. Sometimes what people do in the sciences is they take all of their nonlinear equations and they do this to them. They linearize them, they're good approximations locally, and they solve their entire system with those linear equations. So that's kind of the idea of why calculus is so interested in these ideas. I thought before we end class today, let's try all of this. In fact, the part where we say best linear approximation with applied problem. That's what the homework problem is going to be based off. And then we'll be coming back to this picture a couple times as we get further and further to calculating m. Any questions first so far, folks? Okay, so here's our applied example with this information. When we say average velocity, we're really thinking slope of the secant line. Let me double check I put that in blue. Yes. When we say average velocity, think in your mind, those are the m hat values. Calculating it is not too bad. We just say average velocity is going to be the change in position divided by the elapsed time. I'm not going to use x's. If it's time, I'll be using t's for the independent variable, but same kind of idea. In fact, let's add a little bit more here. This all sounds fancy, average velocities, slopes of secant lines, but they're all really just slopes. We could say this is equal to m. We really want to emphasize that. Sometimes it's best to just remind ourselves we're dealing with a slope, just like we saw in the prior graphics. Calculation of a slope would be f of t2 minus f of t1 divided by t2 minus t1. Or you might have said y2 minus y1, those are the output values, divided by t2 minus t1. I'm emphasizing the function notation a little bit more since so does the course as well, the textbook as well. So it's good to see it this way. Whether you say f of t2, f of t1, recall always that y is f of x, You're just discussing a y value, really. So average velocity is a slope computation. And instantaneous velocity, when you see this word right here, think of, let me try a different way to highlight it. Think of the m hat. Excuse me, I said that wrong. Think of m. The slope of the tangent line is what we're trying to calculate right here. So where it says m is the slope of this tangent line, instantaneous velocity will be that quantity as well. So that's the setup so far. It says the instantaneous velocity of a moving object at time t is the limiting value of the average velocities, these slopes right here, slopes of secant lines, over time intervals of the form t plus h, where h gets smaller and smaller. That interval t to t plus h, that's exactly what we're looking at right here, a to a plus h, just a instead of t. Well, that's the setup so far. I think we're ready to do an actual bona fide problem, similar to what you'll see in the homework. Any questions at all, folks, about the two definitions? Okay, so here's our big example then. It says, a rock is thrown upward on the planet Mars with a velocity of 10 meters per second initially. I don't know the gravity due to acceleration on Mars, but we don't have to do any physics here. They provide us with the equation of motion right here. So y is going to be the height in meters after t seconds have elapsed. It's quadratic, so it looks pretty plausible. Already this might feel kind of strange because I have a y function. This is saying find average velocity. Remember, y is f of x. This is the formula I'm using right here. And so if it's just a helpful reminder, it's not a bad idea to just put in here f of t equals 10t minus 1.86 t squared. So that's just a reminder how we're moving through the formula right here to calculate all of our average velocities. We're going to do it first at 0.1 seconds, 0.01 seconds, and 0.001 seconds after time is 4 seconds. Well, any questions at all, folks, before we start breaking down this problem? Okay, if this is a bona fide homework problem, I would say a good advice to get starting is just figure out anything you can about the problem. We were provided with a strange function, so visualizing it can keep you on a good track of solving this. Let's start by just plotting that function. I'll put in f of t equals 10t minus 1.86 t squared. You don't have to do this for full credit unless an exercise says a graphics required. That should be pretty rare in this class. We have a time condition, so I'll say 0 less than or equal to, it's really hard, less than or equal to t, less than or equal to, let's just say 5 seconds. And that curve right here, that parabola, that's going to be the height at any time t, after the rock was thrown upwards. Let me make that a little bit bigger while we're looking at it. At 4 seconds, we're right here. It's going at 10.24 meters. It's at height 10.24 meters, rather. And so we also know that beyond 4 seconds, it's going down. Let's take a snapshot of this. Again, this is only for illustrative purposes. This is our curve. We'll throw it on the notes and go from there. Geez, that copy is really weird. I forget I'm zoomed in a lot too. Could probably shrink that down. Now, part A says we're going to find the average velocity on a time period beginning when t is 4 seconds. Sorry, getting used to working the system again. And lasting up to 0.1 seconds. And then we'll do it again for the other values here. I'm only highlighting in yellow just to show you what part of the problem we're running through right now. Average velocity, we'll write out, I'll just say average velocity in this way, AVE for average, vel for velocity. And first thing I'll start writing is, we have our function here, we have our time that we're going to begin with, our time we're going to end with. So I'll say f at 4.1. So that's our later time. That's the f of t2 there. The reason I got the 0.1 is starts at 4 seconds and only lasts till 4.1 second. Any questions about that so far? Okay, so that's my f of t2 minus f of the initial time. That'd just be minus f of 4. These are the two time values. So down the denominator, it's t2 minus t1. So that's going to be 4.1 minus 4. Now, if this was an exam problem, this is the moment where we're grabbing calculators and things like that. If I'm being completely honest, I really don't like calculator problems on exams. I'm opening up calculators just because it feels like the right thing to do. It's less stressful for sure. I would probably never put this question on an exam. This is more a homework kind of problem. We have to do lots of calculations and potentially use a calculator as well. So let's work it out. First thing we need is f at 4.1. There's a lot of ways to calculate that. But let me show you slightly longer, but completely valid way of doing it. And I'll show you some shortcuts right after. So pretend that this field right here is your TI-30XA or the other version. And it says f of 4.1. I'm just putting 4.1 in this location and that location, squaring it. So you could just type it left from right, 10 by 4.1 minus 1.86. Oh, that's going to be a problem. 1.86 by 4.1 squared. Tells me the value comes out as a 9.7334. So I'll just throw that in. Yeah, this is not the fastest way to calculate in there, but it gets the job done. So no big deal. Next, I want to calculate, let me move my windows around, f at 4. So I'm at this location. That's fast because we have the function in there already, right? We could just go 4.0, 4.0, and now we have it exactly. It's 10.24. So I'll throw a 10.24 into that location. And that's the numerator. Sorry, say again? Absolutely, yeah. I like that way of going as well. That's a great way to go. Other questions at the moment? Awesome. Doing it this way, it's not the best, it's not the fastest, but sometimes I like doing it the hard way at least once because at least it's a paper trail in the notes, right? You know where the numbers came from. You don't just get a mysterious figure out of there. If you're doing this as a homework problem, I'm not massively concerned about arithmetic. Simplifying things algebraically is part of the class, but this kind of stuff, I'd say do it as fast as you can, so you can focus on the actual calculus, the more interesting kind of stuff. So if you know a shortcut, you're welcome to take it, if it's just number crunching like this. Well, the denominator is going to be 4.1 minus 4, so a 0.1. So now finally, let me do the whole thing. I'm just going to type it all in like a savage. 9.7. Oh, I forgot to go to 5 on that. Okay, 9.7334 minus 10.24 divide by 0.1. So that gives us a value of negative 5.066. Let me put it down here. Negative 5.066. This has units itself. The horizontal axis was time, the vertical axis was meters, and so this will be in meters per second. The negative here is telling us the object is going downwards. So if we know the graph and where we're at 4 seconds, we're right about here. Hey, that looks plausible. The rock is coming back down in height. So we should be expecting negative quantities. Remember, this wasn't an instantaneous, this was like a secant line. That's an approximation of the slope. We want it dead on exact by any way necessary. So if this is a rough approximation, only way to make it a better one is make the time interval small. The t plus h, where h gets smaller and smaller, is manifested this way. I'm not going to go from 4.1 to 4 seconds. I'm going to go from 4.01 to 4 seconds in the next one and get a more refined answer. So obviously, you could spend like a half an hour of all the little clickings on the calculator to get this through. So let's do this one a little bit faster. This is part I. Let's go double I. I'll call this average velocity. If you call this just m because it's a slope, that's a perfectly way to say it as well. I'm going to write this in just to say, what am I calculating? it's going to be f at 4.01 minus f at 4. And then the denominator, well, it's just going to be 0.01, but to show the full formula, we can write it out this way. 4.01 minus 4. Now we're just going to directly get a value out. So in Desmos, if you've programmed the function in already, that's extremely powerful. You can just go down here and say, I want extra parentheses just for the numerator, f at 4.01 minus f at 4, divide by, it's really just 0.01, and that's our quantity. About as fast as I could get it through Desmos. So it's still negative. We like that. The object is still going down, but it looks like it's more refined. We're getting something that's just a little bit different from this, negative 4.8986. Meters per second. I'm not super picky on units. When they do matter, it's probably an interpretative problem. We're just writing words and nothing else. And I'll always say in the problem, units are required. But if you can put in units to applied problem, just as a rule, it is actually helpful. It helps us understand if the number even makes any sense if you're thinking in terms of the units. So now this is still not the instantaneous velocity. Let's go to an even finer time interval, and there's no end to this precision, right? We can make exactly. We're putting in as many zeros as you like, and the numbers we are getting, it may settle to something, or it could become unstable. It could blow up, getting larger and larger. It could oscillate, do all sorts of things. If we're starting to settle down on a number, as we make these intervals smaller and smaller and smaller without bound, we might say there is an instantaneous velocity, and it's the limiting value as we make h smaller and smaller and smaller. So it's all about limits, and that's what this topic is trying to introduce, really. Let's try it one more time. Let me move the yellow. We're going to go from 4 seconds to 1,000th of a second, so that's very precise. I'll call this 3 to just say that's where that portion is being answered. Average velocity is now the function at 4.001 minus the function at time 4 seconds. 4.001 minus 4. And I think I need a new line. Let me drop it below. Running this through one more time. Well, if you did it this way in parts 2, it's even faster, right? Just put an extra 0 right there. Done. Extra 0 right there. Done. It matches this exactly. And there's a number. Negative 4.8816. Let me call it negative 4.8819. Meters per second. Again, it should be negative. We're going down as we go beyond time is 4 seconds. But notice what's happening. We start at negative 5.066 meters per second. I'm going to zoom up real quick. That's kind of like getting the slope of this secant line. It's not very precise, but it's in the neighborhood. It looks close, geometrically by the sketch at least. But as the blue dot gets closer and closer to the green dot, we hope our values settle down on the unknown, the true slope, which is the actual instantaneous velocity. Looking at our figures, we went at 0.01 seconds. It dropped down to this value. We went even shorter as a time interval at 0.001 seconds. Notice it did not budge too much. It might, in fact, be settling down at something around this value. We're going to do something uncomfortable today and not calculate it exactly. That's coming up when we do limits, but we're going to estimate it. You'll have the opportunity to do it the same in the homework. If your estimate makes sense, you get full credit. So I wouldn't worry too much. And if you're not sure, you're always welcome to email. So that's our part B right down below. Part B says, estimate the instantaneous velocity when time is 4 seconds. I'm reminding myself here with the red. Red has a meaning, and my notes, sorry, I have a weird thing I need to hide. My notes had a problem. I did have to revise them, and anytime I do revisions, I'll always put them in that red right there, so you know something's changed. Particularly if you had to print this out early before I caught this myself this morning, you'll know I changed it right there to make the problem make sense, probably. So we need a value at 4 seconds. You could just look at what's happening here and guess, or we have computation available at our fingertips. Let's put an extra 0. Above and below, same amount. Now we're at negative 4.88. Pretty close to this one, and I got an extra 0. So it seems to be stabling out. Let's add maybe 3 zeros. Let's go a little nuts on this one. 1, 2, 3. 1, 2, 3. At 3 zeros, I'm at negative 4.88. Everything after looks like it's zeroing out. Now, this doesn't mean I have the exact value, but it means we can probably put down a good estimate. How about negative 4.88? Does that make sense to folks as a decent ballpark estimate? Awesome. There's nothing to tell us that's exact. This is the scary part of this kind of analysis. It really is a guess and an estimate. It's plausible that this true figure is negative 4.8, 0, 0, 0, 0, 1, 5, and then zeros after, and we just didn't go far enough in the precision here. Other things that are dangerous is, in a numerical computation system like this, dividing by things that approach 0 are unstable. So at certain points, the numerical side of this gets trickier and trickier and trickier. And that's, again, why we're going to be delving into limits quite a lot in chapter 2. But for the moment, let's write this down. Negative 4.88 meters per second. I'll write it this way, just to remind ourselves, instantaneous velocity is a slope. Let's actually be a little more suggestive. Let's go with this color. Oh, geez. Let me try again. So M, I'll put a squiggly line here. That's optional. It's just a reminder for me. I did estimate negative 4.88 meters per second. So that's my claim, that this is how fast that rock was coming down at exactly time 4 seconds. After being thrown upwards at 10 meters per second on Mars. There's a lot of weird context here. Any questions at all, folks, so far? Okay. Now, it turns out this is actually the exact slope. And on part C, it's kind of a bonus part here. Let's see how tangent lines, secant lines, and all those things play together once and for all. We have the graphic of the original thing here. If I can add the tangent line, we'll see what it looks like when technology does it. And they'll support us when we have to do it by hand. The green line here is the tangent line. Occasionally, we do have to do these by hand ourselves. So let's get our favorite equation out. For me, if I have to do a linear equation, and we will do a few of these in class in chapters 2, 3, here and there, I usually go this route. Y minus y1 equals a slope m times, I want to say x minus x1, I caught it this time, but we're using t for time because of the context. So I'll write t minus t1. So if we go this route, notice we've already provided a slope we're going to use on the prior part. I just want to remind myself, what is y1, t1? Or hang on, I have a backwards ordered pair. Let me try one more time with this. I need to know what is t1, y1. I've actually calculated y1 once, but I did not record it. It's on there somewhere. But the t1 is going to be the 4 seconds. The y1 is going to be f at 4. Anyone happen to recall what f at 4 came out as? 10.24? Awesome. And we got that from when we were right here calculating f of 4. Yeah, 10.24. So the value we're going to use is 10.24. Oh, geez, I scribbled. There's buttons on this thing. I have to avoid touching. The 4 right here came from the request. And the 10.24, again, just came from calculating the f at 4. So we can just plug that information here and here. And we get y minus, the y1 is going to be 10.24. Slope n, we have at negative 4.88. Then lastly, t minus 4. So that's our equation. Let me just fix that right here. If you stopped right here on getting your equation for the tangent line, I'm not too worried about that. The trouble with it is it's just not super helpful. There's a lot of computation to get to this point. And what I want to do is plot this line right here to see if it even makes sense in our picture for the graph. To do that, you really want to solve for the line y. So let's just do a little bit of algebra here, maneuver through it. This is y equals negative 4.88t. And now I need negative 4 times 10.24. Way too late in the night for arithmetic. So let me just make sure it comes out right. Negative 10.24 times, and it was negative 4. Getting a figure of 40.96. Oh, I'm multiplying the wrong thing. Let me try again. Arrows might help me out in this situation. I need to multiply that way. I'm going to blame all these windows and moving around. So negative 4.88 by 4 gives me negative 19.52. I'm adding 10.24 across. So this is our tangent line right here. Let me just remind me what color we used. We used green. Let's go back to green on this one. So y equals, sorry, go ahead. You're absolutely right. Thank you for catching that. Our tangent line was going to look really, really off without that correction. Let me put this in yellow right here. Make sure that's a positive by multiplication, negative by negative. Any other comments so far? Okay, thanks for spotting that. And then we settle at negative 4.88t plus one last addition. We're almost there, folks. I'll get better with these windows as we go. I'm just a little rusty at this. Our computer is actually pretty good, but our projector on the wall keeps us at a very, very small resolution. So it's always a bit of a struggle. So 19.52 plus 10.24. So we get a 29.76. Okay, so this is the moment where we're going to decide, is this really even the right tangent line? Was that a reasonable guess of the instantaneous velocity? If all that's true, then we know quite a lot about that rock. It's falling down at that rate of speed, 4 seconds after it was tossed upwards. So we can go back to Desmos now. First, any questions at all, folks, on obtaining the line? Okay, I'm just going to click these X's to pull these away. We're done with all those computations. We have the original function provided with its domain. Now we add the tangent line. It is y equals negative 4.88t plus 29.76. And this is what tangent line should look like. It should look like right where that gray dot is. The green line is the best linear equation you could ever put to approximate the actual curve in red. There's a unique answer to this. It's kind of amazing. You could do no better than it. And so that's finally our graphic. Put that on the notes just to kind of finish it off. But I want to return to one last comment in our initial definition, which is extremely confusing. At our initial definition, we said it is the best, that tangent line is the best linear approximation near the point in question. For us, it was time 4 seconds and the height at 4 seconds. And let's now explore, why is that the best approximation? Well, in Desmos, if I zoom in right at that point of intersection, right at 4 seconds, the green line and the red line, they're going to become indiscernible. See that happen? Right around here, I can't tell the difference. Maybe down here, there's some fringing that you might be able to see. But the pixel width is too big to show the difference between the lines. Now, what would happen if we made a mistake? Let's say we guess negative 4.89. Big problems, right? That's not a tangent line. It actually has to intersect at times 4 seconds. So it should have been 8/8 right here. And if my dyslexia manifested and I said 6/7, that's not going to work either. It has to be exactly dead on precise for it to really look like a tangent line. Any small mistake that you made, even if it was a small algebraic mistake, sure might look like right here, but it's actually the wrong tangent line. You investigate further and further in. Oh dear, I was not where I thought I'd be. Zooming gets a little bit tedious. There it is after a while. But that's the ideas that we're going to be exploring all class. The takeaway of all this is it's nice to be able to estimate that number right here, which allowed us to produce the tangent line. But this problem is rigged. It's a fluke that it came out exactly the way we wanted. That could have been an irrational number, a non-repeating decimal. It could have been something pretty nasty. And if we're just using numerical methods like these, we're not going to find the exact value if we need an exact value. So we're going to be taking several weeks and talking about limits, the limiting process, and see how that all ties together to get us back to M. We'll later call it a derivative. Well, any questions, folks, or comments about any of this stuff so far? Okay, well, to wrap up, today's class wasn't meant to go to 8:07. That's a hard time to hit, but I'll try to hit that the best I can. What I'll be doing after class today, or probably more Tuesday morning, is I'm going to add some information on assignment 1 so that you'll know what does exercise 5 look like. I'm going to provide it to the class so you can get started right away without waiting for your book. I'm also going to update this so it's the actual file of solutions. Keep looking here for lecture notes for, say, section 2.2 before Wednesday. And depending on how you do the class, you might find it valuable to print them out and just fill them down as worksheets. If you work digitally and you're not opposed to that, you could download them and just draw on them and save them. Or traditional notes is going to work really fine for this class as well. It's all going to be up to your preference. Well, any last questions or comments, folks, before we call it a night? Okay, well, if you have any questions, feel free to see me down below. I'll be happy to help out. I'm not saying that every single night, but it's always a standing offer. If you have questions, feel free to stick around. Otherwise, drive safe. I'll see you all on Wednesday's class. Well, maybe one small thing. I need to stop the recording after class is over. So if you do have questions, and if they're of a nature you never would want to see on the internet, like, what's my grade? You don't want to throw that on the internet. Make sure I did these steps right here.